Welcome to the third installment of the digestive system lecture. This is where we're going to cover a lot of the accessory organs and more on the physiology of digestion and absorption. So the next topic is going to be on liver, gallbladder, and pancreas, and how these three organs function to aid in digestion of nutrients. So we'll start with the liver. The liver is made out of cells called hepatocytes, and hepatocytes are cuboidal cells that actually have three major roles: absorption, removing, and secreting things from blood. The hepatocytes are able to absorb things like glucose and store it in the liver as glycogen. They're able to absorb amino acids, iron, and vitamin from the blood. And at the same time, these cells can remove and degrade things that are toxic. Things like hormones, toxins, bile, pigments, and drugs. And it also includes things like alcohol. When these cells are overworked in filtering out and removing alcohol, that can cause something called liver cirrhosis to happen, ultimately leading to liver cancer. The last function is to secrete things into the blood. And hepatocytes create and secrete albumin, which is a plasma protein that we talked about when we talked about the cardiovascular system, lipoproteins, clotting factors that actually help you clot blood inside and outside your body, and angiotensinogen, which we saw was the precursor inactive version of angiotensin. So what does this look like in terms of relation to other organs? So if I get my pen out here, we will draw where the liver would be. The liver would be here. It sits on top of the gallbladder, and then your stomach would be here, right there. So chyme from the stomach would pass the pyloric sphincter here and enter into the duodenum. Once this chyme, and we'll draw it as like a ball right here, enters into the duodenum, signals are sent to the liver, to the gallbladder, and to the pancreas to let them know that chyme has arrived. This is because when chyme arrives, you should start secreting out things like bile from the gallbladder, things like pancreatic juices from the pancreas. Notice that both the bile duct and the pancreatic duct converge right over here before secreting out into this first part of the small intestine called the duodenum. This is where all of those pancreatic juices, the bile, are able to mix with the chyme to start the big digestive process. So we said the liver makes the bile and the gallbladder stores the bile. So what is bile on its own? Well, bile is a greenish yellowish color. It is a fluid, and it's made out of cholesterols, fats, phospholipid, bile pigments, and bile acids. The purpose of bile is to help emulsify fat. The word emulsify means to take a very large globule of fat and break it into smaller, little tiny globules we call micelles. So we'll see an illustration of this when we talk about fat digestion and absorption towards the end of this PowerPoint. But what's in red here is the term bile salt. Bile salts, that is the active component of bile that actually helps to emulsify the fat. Bile salts are made up of a hydrophobic portion and a hydrophilic portion. The hydrophobic portion of a bile salt is what actually interacts with the large fat globule. Now there's also bilirubin. This is what makes fecal matter brown. And then you can have a buildup of cholesterol in your gallbladder, and that can lead to gallstones. And then the third organ, the pancreas. The pancreas is very, very special. It's probably one of my favorite organs because it has multiple functions. The two main roles that it plays is it's an endocrine role and the exocrine role. The endocrine role of the pancreas is the hormonal role, and that's what secretes insulin and glucagon. And those are the two hormones that help to regulate sugar. The exocrine role, and the role that we're going to talk about today in this PowerPoint, is the enzymatic role. The pancreas produces a slurry of enzymes that it then secretes into the duodenum. Those enzymes, their job is to digest nutrients that come in through your digestive system. We will talk about all the enzyme names and all of their functions. Now, what's in red, underlined, and bolded here is something that I really, really want you to understand. There's not very many details in terms of enzyme names, but this is like the big picture of the pancreas. So the pancreas makes something called a pancreatic juice. This pancreatic juice is what gets secreted into the duodenum, and it's made of water, enzymes, zymogens, so inactive enzymes, sodium bicarbonate, a buffer, and other electrolytes. The first term is an alkaline mixture of all this. What does the word alkaline mean? It means basic. So if we look back to this illustration, you'll notice that the chyme that's entering into the duodenum is coming straight from the stomach. So as you can imagine, it's going to be very acidic. That acidity can damage the internal lining of the duodenum. So the pancreas produces an alkaline mixture to mix in the duodenum with that acidic chyme. So acidic chyme mixed with the alkaline pancreatic juice will create a sort of neutralized solution. So the fact that it's alkaline is very, very important, and the fact that we also secrete buffers in there help to regulate that neutral environment. This is one of the branches inside the pancreas. You'll notice it's made out of two different cells. You've got acinar cells right over here, and the acinar cells are going to be what secrete the enzymes and zymogens. This branch of cells, the lining of cells, is called your duct cells. These are the cells that make bicarbonate, so the buffer to help buffer out that acid coming into the duodenum. Now I'm going to get my pen and I'm going to underline a few very, very important things that I really need you to know. So here's where I start listing the enzyme names and their functions. The first thing that I want to remind you all is that proteins are made out of amino acids. And let's connect these proteins with peptide bonds. On one side of an amino acid chain, you have a carboxyl group, COOH. And on the other side of the amino acid chain, you have what's called an amino group, NH3+. So you have the amino side, the carboxyl side, and you have peptide bonds in the middle. This is going to be important to know when we talk about the functions of some of the enzymes that are produced by the pancreas. So I told you the pancreas makes enzymes that are active, but it also makes zymogens, an inactive version of an enzyme. There are 3 zymogens we make. Make sure to know these 3 zymogens. The first zymogen is called trypsinogen. And the role of trypsinogen is to get converted into one called trypsin. So trypsinogen gets converted into the active form called trypsin by an enzyme called enterokinase. Enterokinase is an enzyme that converts trypsinogen into the active form trypsin, and we'll talk about trypsin's role a little bit more later. Trypsin itself has a role in activating other enzymes that are found with it. Trypsin can activate chymotrypsinogen into chymotrypsin, and it also converts procarboxypeptidase into carboxypeptidase. So the 3 zymogens produced by the pancreas are trypsinogen, chymotrypsinogen, and procarboxypeptidase. Trypsinogen converts into its active form called trypsin with an enzyme called enterokinase. And when you activate trypsinogen into trypsin, he can then act as his own type of activation enzyme, converting chymotrypsinogen into its active form and converting procarboxypeptidase into its active form. We are going to see an illustration of all of this in just a moment. The other enzymes that are made by the pancreas that are just simply active enzymes are going to be pancreatic amylase, which break down starches, pancreatic lipase, which break down lipids, and ribonuclease and deoxyribonuclease, which break down DNA and RNA. So here's that illustration that we talked about, and we're going to start at the pancreas. The pancreas makes trypsinogen, chymotrypsinogen, and procarboxypeptidase. All three of these are in their inactive forms, but how do we activate them? Well, inside the duodenum, which is where this is, do you see all these little cells that line the duodenum? These are called enteroendocrine cells. If we go back a slide, that word is not here, but if I could add it anywhere, it would be right here. This is an enzyme secreted by the mucosa of the small intestine by cells called enteroendocrine cells. So just fill it in right there. Enteroendocrine cells. That's going to be these little cells that are on the border here. So these enteroendocrine cells will make an enzyme called enterokinase. The job of enterokinase is to convert trypsinogen into trypsin. So you've now activated one of the zymogens. This trypsin can do two things now. It can go and activate the other two zymogens into their active form, so chymotrypsinogen into chymotrypsin, and procarboxypeptidase into carboxypeptidase. Trypsin can also autocatalyze its own reaction. So the more trypsin you make, the more you can catalyze more trypsinogen into trypsin. It has an autocatalytic effect. If you struggle with this slide, please make sure to put a star on it and contact me for explanation. So make sure to know this slide. I already wrote know this on the top in bold. And why I want you to know this slide is because this is how you regulate what and how much the pancreas and bile secrete. There are three main stimuli. Acetylcholine. Remember, there is a nerve called the vagus nerve, and the vagus nerve is the rest and digest nerve. When you activate the vagus nerve not only slows down your heart rate, but it's able to also stimulate and upregulate the digestive function. And it does that by secreting acetylcholine onto those digestive organs. When the vagus nerve secretes acetylcholine onto the stomach or the pancreas, you're going to stimulate those organs. So when this acetylcholine is secreted onto the pancreas, it activates the pancreas to secrete enzymes all the way up during the cephalic phase. Now, if you remember, the cephalic phase is just the phase where you're simply thinking about food. Maybe you're looking at food and you're smelling food, but you definitely haven't eaten it yet. At that point, you are actually activating the parasympathetic nervous response, and that can activate the vagus nerve to release acetylcholine onto the pancreas to make their enzyme. So you're already starting to make enzyme from the pancreas even before you've eaten food. The next one is CCK. This is one that you've seen. CCK is made by the duodenum, and it's made when the duodenum senses the arrival of fats in its lumen. So when that fat arrives into the lumen of the duodenum will make CCK, and that CCK sends a signal to two different places. It sends a signal to the pancreas to secrete enzyme, and it stimulates the gallbladder to secrete bile. The last stimulus for pancreatic juices and bile is secretin. When acidic chyme comes in from the stomach, the acidity is now the stimulus in the duodenum to secrete secretin. Secretin will stimulate the liver and the pancreas to make more sodium bicarbonate. So if you think about it, it kind of makes sense. Because there's more acidic chyme in the duodenum says, uh-oh, that pH just dropped. That's not very comfortable for me as the duodenum, because as the duodenum, I like to be slightly basic, maybe a pH of 8 or 9. But now we have all this acid coming in from the stomach. Well, what are we going to do to prevent damage? All right, let's tell the liver and pancreas, make more bicarbonate. That bicarbonate acts as a pH regulator and a buffer to help raise the pH back to a somewhat neutral rather than acidic level for the pancreas. For the duodenum. Now, this is the illustration that ties everything in together. I'm going to go through it step by step, and I will actually number it for you because I know a lot of you guys like when things are numbered. So we'll start at the stomach, and the stomach has chyme in it. The chyme ends up going into the duodenum. This chyme is acidic, and it has partially digested fats, proteins, and carbohydrates in it at this point. The arrival of the acidic chyme that also has partially digested fats in it is going to stimulate secretion of CCK and secretin. Now, I'm just going to number these arbitrarily. It doesn't mean it happens in this order, but it'll keep you organized. One of the jobs of CCK, and we'll number it number 1, is to stimulate the gallbladder to secrete bile. The second job of CCK is to stimulate the pancreas to secrete enzymes. And the last job of CCK up here in red is to down-regulate the stomach, to say, hey stomach, we've received your chyme, you can decrease your gastric secretions now. And so we'll number that number 3. In addition to creating CCK and secreting it, the duodenum makes something called secretin. Secretin will go and it will, as number 4, stimulate the pancreas to create sodium bicarbonate. It will also go to the stomach to, again, we'll number that number 5, down-regulate the stomach. So far CCK and secretin, we got this one, the CCK up here, which goes to number 3, number 4 secretin, and number 5 secretin. The only other thing here is gastrin. When the stomach's not completely empty, and if there is presence of partially digested proteins in here, that is going to cause secretion of gastrin, and gastrin will upregulate the stomach until the stomach is completely empty. So all of this now is part of regulation of the liver, gallbladder, pancreas, and stomach. And so far we've talked about gastrin, CCK, and secretin. Now, the small intestine is broken up into 3 regions: the duodenum, the jejunum, and the ileum. So far we've only talked about the duodenum because that's where the pancreas secretes its juices. So the duodenum will begin at the pyloric valve, which is directly connected to the stomach, and it receives all the stomach contents, it receives the bile, and it receives the pancreatic juice. It is in this location that you need bicarbonate to neutralize the incoming chyme. This is also where fats are emulsified because this is where bile is first interacting with your chyme. Remember, one of the big jobs of bile is to emulsify fat. That means to take a big glob of fat and break it down into smaller pieces. The pepsin that was active in the stomach is now inactive because pepsin likes to be at a pH of 2 rather than a higher, more basic pH like that of the duodenum. And not a problem though, because pancreatic enzymes are being secreted to now take over all the digestion. The jejunum is right after the duodenum. The jejunum, the big thing here is that it is highly vascular. Highly vascular. Once you mix together all the chyme, the bile, the pancreatic juices, this is where you start almost all your digestion. The remainder where you have the jejunum, is where you complete most of your digestion. And because it's highly vascular, meaning there's a lot of blood supply, it is in the jejunum that you're going to absorb all that nutrients into the blood. And again, it's because the jejunum is highly vascular. If you recall on the cadaver, maybe your teacher pointed this out to you, but the jejunum is a much darker red region of the small intestine because of that vascularization. At the end, you have the ileum, and the ileum is where you're going to find Peyer's patches. Peyer's patches are part of the lymphatic system. They're lymph nodes. And if you know a lot about lymph nodes, or even if you know a little bit about lymph nodes are part of your immune system response. And so they help with an immune response of what you've eaten, digested, and at this point absorbed. Now this is a fill in the blank. In the small intestine, you do have these ridges that you see here. These ridges have little hair sticking out of them called villi. If I take one of these villi and I look at it here, so this is one villi, that's one of these little fingerling projections. Take a villi and you'll see that it's covered with all these little columnar cells, okay? This is considered the epithelium of the lumen. Inside this one little fingerling, you have a little capillary bed with this yellow thing going in the middle of it. What is that yellow thing? Well, that yellow thing is called a lacteal. So you have the intestinal ridges that are covered with villi. This villi is covered with epithelial cells, and inside of the villi is a capillary bed and a lacteal. A lacteal is a specialized lymphatic vessel in the digestive system responsible for absorption of fat. So it is a specialized lymphatic vessel in the digestive system responsible for the absorption of fats. Now, if we take just one of these epithelial cells and look at it, at the top you see even more finger-like projections called microvilli. Micro means tiny. So not only do you have the villi, but on top of those villi, you have microvilli. What do you think you're increasing inside the lumen of this small intestine by having microvilli on top of the villi, on top of all of these ridges in the intestine? Well, you're increasing surface area. The more surface area you have, the more absorption of nutrients you can do from inside the small intestine across the membrane of the epithelium to be absorbed by either your blood circulation or, if you're a fat, the lacteal. So that surface area, increasing it, is a really big deal in absorption of nutrients in your body. So we call this area where you have the villi and the microvilli, we call it the brush border because it looks like a hairbrush. You got a lot of little bristles sticking out. This brush border is going to, number one, increase surface area like we talked about, but it has a second job. So if I get my pen here, I'm going to number them, number 1 and 2. So this is number 1, having a brush border, and number 2, having brush border enzymes. These cells here create enzymes that stay within the forest of this brush border. They don't go out into the open space. They stay within the brush border. They're called brush border enzymes. And for the chyme, let's put the chyme into like this ball right here. As this chyme is making its way through the small intestine, the perimeter of the chyme needs to come into contact with this brush border in order to gain the benefits of these enzymes. This is called contact digestion. This is one of the big reasons why your small intestine churns and contracts and spins and churns longitudinally, laterally, in every direction to make sure that this chyme is able to come into contact with those brush border enzymes. You'll see examples of these brush border enzymes soon, but I want to make sure everyone understands that brush border enzymes are a group of enzymes that are found within this brush border. They do not come out into the lumen. They stay in the brush border amongst the villi. So again, we said that it's important for the intestine to churn and mix its contents to get those chymes in contact with the brush border enzymes. So intestinal motility happens, number one, to mix the chyme. And you're mixing the chyme with brush border enzymes, with pancreatic juices, and with bile, and helps to neutralize those acids as well. And it's also there to churn the chyme and bring it in contact with the brush border. Lastly, of course, you have to move that chyme through the duodenum, through the jejunum, through the ileum, and towards the large intestine. Now, there is a term here called segmentation. Segmentation is a type of smooth muscle contraction. If you see that it kind of squeezes little indentations into the chyme. It splits the chyme into little bite-sized pieces. Segmentation, they're stationary contractions where their job is not to move the chyme from point A to point B, but their job is to mix the chyme in place. This mixing happens with pacemaker cells. We've talked about pacemaker cells when we talk about the heart and its contractions, but pacemaker cells that are found in the small intestine are just simply smooth muscle cells that create a pace of creating junctions in between the chyme, mixing it in place, and it's consistently doing this at a consistent pace. It is a rhythm that is set by these smooth muscle cells. So it doesn't move food forward, it just churns it in place. However, there is a type of movement that moves food forward. We talked about this when we talked about the esophagus, and that term is peristalsis. The job of peristalsis is not to churn the food in place. It is to push the food forward in a wave-like fashion. So it's smooth muscle contractions that are lateral. These peristaltic waves in the small intestine will start in the duodenum, and they'll make their way all the way through the jejunum and the ileum. At the end of the ileum, you have this valve called the ileocecal valve. It really is just what the name states. It's a valve that's found between the ileum and the cecum. So this is the valve that opens and closes to control how much chyme goes from the ileum into the cecum. And this is the point in the lecture where we're going to really dive in to a lot of the physiology.